Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And so we talked yesterday about wind shear and the hodograph and all of that and its contribution to severe weather and tornado potential. And now today we talk about the other main element, and that is what we call instability. And the technical term for it in meteorology is an acronym called CAPE, C-A-P-E, which stands for Convective Available Potential Energy. So that's what we're going to be talking about today. And trying to make this lighthearted here, I said, does the atmosphere need counseling? Well, if the atmosphere was unstable, then maybe that would be helpful, but obviously the atmosphere doesn't have a personality. So anyways, all right, so let me go on ahead and put myself down here in the corner and let's get started. Okay, so there's a couple of different ways to look at stable versus unstable. Supposing that you had a raindrop, and I know they're not shaped like this, but just for the purpose of this example, and the raindrop is going to start to grow in size, and once that growth starts, it's not going to stop. It's just going to go on and on and on and on until some process actually ceases that trend. So the raindrop again grows and grows and grows and grows, never to return to its original size. However, supposing we have a situation like this where we start off with the same raindrop and it starts to grow, but then something happens where it's no longer favored to grow anymore and it shrinks back to its original size. That's what we call a stable situation, where it starts to grow, but then it says, oops, I'm not in a good place here. I want to go back to where I started, okay? Now, if we look at this in terms of air parcels, okay, let's have two of them here at the bottom. And the first one is going to rise, and then it's going to have something happen to it, and we'll talk more about this in a second, which is going to make it stop rising, and then it's going to go back and return to its initial position. So that again would be a stable setup. The one on the right though, once it starts to go up, it's just going to accelerate more and more and more and keep going up, and this would be a situation that would be unstable and would lead to the development of those big puffy cumulus clouds, and sometimes in the summertime they can get 50, 60,000 feet high. So that's the kind of scenario that you would have with that. Okay, so some definitions. Force is equal to mass times acceleration. Okay, so if there's a force, there has to be an acceleration because the mass is going to be constant. Buoyancy is defined, and this is from the American Meteorological Society glossary. Buoyancy is defined as the upward force exerted upon a parcel of fluid in a gravitational field by virtue of the density difference between the parcel and that of the surrounding fluid. So you have the atmosphere, which is the surrounding fluid, and you have an air parcel within that. And this force is exerted on that air parcel within the larger environment. So if an air parcel becomes buoyant, it will accelerate upward as long as it is warmer than its environment, okay? And the greater the buoyancy, the greater the force, and the more rapid the acceleration. Okay, so let's take a look at a couple of examples here. So supposing the weather balloon goes up over Raleigh, Greensboro, whatever, and the temperature decreases with height, and then there's a really steep inversion where the temperature actually goes up with height, right in this area here, and then it begins to decline again as you go up. So if you have an air parcel that starts off here and you heat it up and it's just a little bit warmer than its environment, then it starts to rise, but then all of a sudden it finds itself colder than the environment that it's in, and it says, ooh, I don't like this, and it just goes right back to its original position, okay? So that would be a stable scenario. An unstable scenario would be one where maybe you don't have that inversion at all. The temperatures decrease with height all the way up to what we call the tropopause, where it's the end of the troposphere and you're beginning to head into the stratosphere, and temperatures start to rise with height up there. But we're talking about way, way up where that happens. So remember, the air parcel is going to cool at the dry adiabatic lapse rate until it becomes saturated. And at that point, it begins releasing what we call latent heat. And so now it doesn't cool as rapidly as it was when it was unsaturated. So in this situation, the parcel would rise like so. And then once that condensation occurs, then it cools at a less rapid rate, right? Yes, cools at a less rapid rate. And so it becomes even more buoyant, and it doesn't stop going up until it gets up to that inversion at the top of the troposphere. And even then, you know, when it becomes colder than its environment, it doesn't stop. It simply stops accelerating and starts decelerating. So it continues to go up even after it becomes colder than its environment. It just is no longer going up at a faster and faster clip. It's going up at a slower and slower clip, and eventually it is going to come to a stop. Okay, so that's the basic difference. And a lot of times what happens out in the nation's midsection, and this is why, you know, many of the violent tornadoes occur there, is that in the Rockies, you figure that some of those mountains are, you know, 8, 10, 12, 14,000 feet high. And the land surface on the top of those mountains is being heated, okay? And so that warm air in the mid-levels of the atmosphere gets out over the Great Plains. And the lapse rate from that point up is huge, okay? Because it's just like us setting up the same scenario at the ground, where it's going to be a very steep lapse rate over the layer that the atmosphere is well mixed. And so when you're starting off that high, then you have the same scenario. It's just that now it's starting in the mid-levels and going up to the upper levels. And so when that air gets out over the plains, initially there may be a little bit of what we call a cap, you know, where the temperature goes up a little bit with height before it starts that really steep lapse rate. But if something comes along to remove that cap, like a disturbance in the upper atmosphere that causes large-scale upward motion, and upward motion cools the overall atmosphere, it's almost like you have a tire that is being overinflated. And then all of a sudden, somebody pokes a small hole in that tire and the air comes rushing out like mad, okay? So it's the same principle, is that you can build up all this hot, humid air underneath this cap, and it's just building and building and building and building, and then something comes along to remove that cap, and it just explodes. And there was an outbreak in Ohio back, I believe it was May 31st of '85, where it went from being totally sunny to tornado warnings in an hour. And that was a situation where they had a pretty strong cap, kept it sunny all day long, but boy, once that cap was removed, all heck broke loose, and it can happen very, very fast. So that's another example of what can happen with this idea of instability. All right, I hope that made a little bit of sense. That is bonus weather video number 2 for this week. Number 3 will be coming up on Friday. Next daily update, of course, coming up tomorrow. So y'all take care, folks. We'll talk to you soon. See ya.